Hello everyone, I am Karthik from ITA section. My roll number is 20951A1230. On today on Tech Talk, my topic is about moment generating function of non-Markov self-excited claims process. Let us see what is non-Markov self-excited state process and how is a moment generating function will displace. Let us see in the further slide. Introduction to it is a self-excited process or a natural solutions to introduce a contagion between claims. In this approach, the occurrence of a claims depend on previous ones. This dynamic was initially introduced by Hawkes in 1971 and Hawks and Oaks in the most common specification. The intensity of a claim numbers that is akin to an instantaneous probability of a claim increases as soon claim is observed. The influence of this claim on the intensity next decays with the time according to a memory function also called kernel Musmeki and Verne Jones in 1992 or Ogata in 1998 purpose such a point process of earthquake occurring a Potter and White use a similar self-excited process of modeling an activity. Barsotti et al. Model the contagion of lapse in the life insurance with exponential self-excited process. Hynet introduced contagion between insurance and financial markets with a Baviot self-excited process. More recently, Bessie Ronald et al. 2020 uh, multivariate extension of such processes to cyber claims. The reader may refer to Reinhardt for a detailed review of other applications and properties of Hawkes process. We show that when the memory kernel is the Fourier transform of a measure of probability, the self-excited claims can be reformulated as an init dimensional Markov process. In the complex plane, we focus on the four types of memory kernels associated to Laplace, Gaussian, logistic, and Cauchy measures. Next, we approach the init dimensional Markov model by a night dimensional process and obtain its MGF moment generating function using standard Stokes calculus. The MGF of the init dimensional process is obtained by considering the limit of the night dimensional approximation. As illustration, we exploit these results to compute the probability density function of cyber attacks in USA and medical and other services. A moment generating function. We establish the moment generating function of a claim process by considering the limit of the MGF of the discretized model detailed in the previous section. Firstly, we provide the analytical expression of a QL in the next corollary. The function here we are taking a function and the result is directly proven by checking the proposed expression of E's S solution of the ODEs. Here we are taking the moment generating function and we are substituting the values at the last and by applying limits and integration as a process. LT is the limit of the LT bar. When the n is infinity, we can find its moment generating function by considering the limit of the equation. The next proposition presents the main result of this article, and the moment generating function claims process of E is exponents of q naught t comma s plus q lambda t comma s power t lambda t plus omega t into limit t. Here there are some proofs to prove the moment generating function of a non-Markov self-excited claim process. By doing this, we will get end result. This result may be used to estimate the value of each and all business lines by indifferent pricing. For instance, let us denote u of x equal to minus 1 by lambda e power minus lambda x. The insurer utility function, the initial surplus is S naught, whereas the P of S is the total premium for covering the M risk up to the time S. The surplus at the time S is defined as S naught S equal to S naught plus P of S minus sigma k equal to 1 to M L of S to K. This is how we get the end result. At last we get P of S equal to 1 by lambda log E into e power lambda power e power t into limit of f naught. This is a non-Markov process where uh, uh, this value e into e lambda e power t L of s f naught can be calculated with the proposition which we have done before, in which omega equal to omega lambda into E. Another interesting use of the MGF is a computation of a joint and marginal probability density functions of aggregated claims. The point is developed in the case study concluding the article. But before we focus on the subcategory of Cauchy's memory kernels for which lambda t and LT is t greater than or equal to 0 is Markov. A non-Markov process is an stochastic process that does not exhibit the Markov property. The Markov property, sometimes known as the memoryless property, states that the conditional probability of a future state is only dependent on the present state and is independent of any prior state. Common example used in books introducing Markov chains is that of weather. They say that the chance that is will be sunny, cloudy or rainy tomorrow depends only on what the weather is today, independent of past weather conditions. If we relax this last assumption and said that the weather is dependent on a large range of past weather conditions, and or if we said it was additionally dependent on factors other than the weather, such as time of a year or the amount of the greenhouse gases or whatever, then the process would no longer be a Markovian. Generally, if you are dealing with a stochastic process or situation where you cannot assume that the future state will be dependent only on the present state, it's probably a Markovian process. Is the demand for a product in the next period is based on the external factors other than the demand of the present period, that's a non-Markovian process. If the machine breakdowns are dependent on the entire lifetime of a machine, considering this life like wear out rather than just presenting conditions of the machine, that's a non-Markovian process. If tomorrow's inventory level of a warehouse is dependent on a long-term seasonal conditions and not today's inventory level, that's a non-Markovian process. In statistical process control, if there is an upward trend in defeats, that is probably indicative or underlying assignable cause and thus non-Markovian. Important non-Markovian processes include ARMA, autoregressive moving average, models with at least one of the two orders being greater than 1, and more complicated models in time series such as ARCH and GARCH. All these discrete time processes are intensively used in finance, econometrics, signal processing, etc. Fractional Brobian Brownian motion with Hurst index different from half. This is a continuous time process which behaves locally like a Brownian motion but exhibits a long range dependence. It is used in finance, biology, climatology, among many others. Indeed, if you mix a class of process, then in general you get a Markovian process. That is to say, assume you may have a family of stochastic process called x theta or t, where theta is a chosen from a set. Then if we generate the process by sampling at theta first, then we get the realization of x theta of t for all t. Then the process that we will get probably not be a Markovian, since the history will be helpful in determining theta. Thank you. This is about the non-Markovian process claim. Thank you.